All right, so we just finished doing a discussion of limiting reactant and how that's an application of stoichiometry. And today we're going to do a very specific application of stoichiometry that kind of relates actually to our last two units, you will see. This is a very common analysis that's done through combustion. You have some organic sample, and you remember from organic chemistry, carbon, hydrogen, and a lot of times oxygen. Those are the big three in terms of organic compounds that we can analyze. So what you're able to do upon heating these substances up is you have something that absorbs water very well. You can sort of think of it as a filter that pulls water out of the system. And then we can also pull carbon dioxide out of the system and then analyze the actual amounts of carbon dioxide in water. So we know that those are the three elements that you're usually going to see in an organic compound. So, oops, accidentally went backwards there, sorry about that. Ignore all that stuff. So there's our combustion analysis. So go ahead and write this problem down as we've done with our other problems. And we know that the initial mass is a 2.04 gram sample. So that's something that we could measure out on our scales in the room here. And upon going through that combustion analysis, it's found that there was 4.49 grams of CO2 and 2.45 grams of water. And then it says, find the empirical formula of the compound. Well, we're quite a ways away from being able to do that, because right now you only see an amount of carbon dioxide and an amount of water. How can we turn that into C to the X, H to the Y, O to the Z, given this information? So that's where our good friend stoichiometry is going to come in to help us. All right? So if you think about it, we can convert into grams of carbon and hydrogen based on looking at the stoichiometry, and then we can convert those into moles. And this will be a lot like that assume 100 grams problem, because if we know moles of this, moles of that, and moles of that, we can divide by the smallest and get the empirical formula. And this is where I'm talking about how this relates to the last unit when we did the reverse percent composition problems. But these definitely are different. We're not going to do any percent composition. So the first thing we're going to do is find the mass of carbon. And if you look at that, carbon dioxide and water, so you know those are the two products, you know all the carbon has to come from the carbon dioxide. So that is the big thing that we can use. So you've got CO2 and H2O. The only place there's carbon is in the CO2. So trust your instincts here and get the atomic weight of CO2. Now, I apologize, and I'm not going to go back and make you change anything. So we'll just use the numbers that they have here. But when you do the test, when you do the practice problem, let's stick to our agreement of using the periodic table that was two places to the right, and that would have been 44.01. But you've done enough of those. We'll just use the numbers that they have here. I'm not quite sure why all of a sudden they decided sometimes they go two places to the right, other times they don't. Maybe they are viewing this as more of a crude thing. But anyway, just let that slide. If you were doing this problem on a test, I would expect you to write 44.01 because carbon is 12.01. But just let that slide for right now, so that we can focus on the bigger picture here. Okay, so we'll just use the numbers that they have. Awful darn close, so we'll let that one slide. All right, so that'll happen a couple of times here, and I won't even mention it again. We'll just say get the atomic weights. Now, there is no balanced chemical equation, but you can do a mole-to-mole conversion from the formula. Because if you have a mole of CO2, you would also have a mole of carbon. Now remember, mole is you're counting something. So let's go back to our dozen example. If you had a dozen CO2 molecules, you would have 12 carbon atoms. So 1 mole of carbon per 1 mole of CO2. So that is yet another example of stoichiometry, and that's why I like to show you guys these combustion analysis problems. So the last step, again, 12 grams of carbon, 12.01. You crunch the numbers, you're going to have 3 sig figs. So we have about 1 point. All right, sorry about that. There's a glitch in the matrix and an announcement about the 7th and 8th grade assembly. So anyway, so you're going to get 1.22 grams of carbon. So it's kind of like, figuring out if you have this much CO2, how much of that mass would be carbon. There are other ways that you could approach this, but stoichiometry is a really, really good method to do that, and it's what I'm going to require for you to do on a combustion analysis. So we're going to do now the mass of hydrogen. So we'll continue to use that same type of analysis here. That is the formula weight of water. And now this water's a little bit different, isn't it? If you have a mole of H2O, you actually have 2 moles of hydrogen. Think of it as being smaller parts of the molecule. If you have a mole of cars, you would have 4 moles of tires. So you have 1 mole of water, you have 2 moles of hydrogen. It's the smaller part. So there's a 2-to-1 ratio. No balanced chemical equation. So this is a little different twist. Now remember, you've got this beautiful example to use in your notes when you're doing this. And now we got to get that to grams. So you'd be using 1.008, but they use this. And you end up with 0.27 grams of hydrogen. And you can see how the atomic weight there, using that lesser atomic weight, kind of limited your answer there. So we would have been able to have 3 sig figs in our answer. But we'll follow their sort of reasoning at this point. Now, here's the catch with oxygen. Oxygen is in both CO2, there it is, and O. So you don't really know how much is in each one. You can't really figure out the ratios, but you can figure out the mass of oxygen, because if you go back, you know the total mass of the sample. Okay? So what you can do is take that 2.04 grams, which is the total mass of the sample, and subtract the mass of the carbon and the mass of the hydrogen from it. Real logical, right? You got 3 things, they add up, you know 2 of them, and you know the total. You can just do the subtraction. So probably not a bad idea to write the steps down here, but I think this is really intuitive. It's something you can figure out kind of on the fly right there. So we now know grams of carbon, hydrogen, and oxygen. So this is where this gets to be just like the assume 100 grams. And instead of assuming 100 grams, you're given the gram amounts. Convert each one of those into moles. Look at what they did there. Now they're back to 2 places to the right. But again, this sig figs is off a little bit. You won't do that on yours. But let's just use this as an example. So you have 0.1 moles of carbon. You have 0.27 moles of hydrogen, and when you divide that out, that pretty much is the same thing. It looks like they're just kind of using 2 sig figs throughout there. And when you divide oxygen, so you're just converting each one into moles by dividing them by their atomic weights. If you do combustion analysis, these are going to be your elements, carbon, hydrogen, and oxygen, when we do these problems. It could be just a hydrocarbon, but usually we throw in some oxygen as well. Okay, so those are kind of weird numbers. You remember the little trick we used was to divide each by the smallest. Okay, so you're going to take that one divided by the smallest. You're going to take that one divided by the smallest, and you'll get a 1 to 8 to 3 ratio. And this is the penalty they pay for rounding those things. Is not as close to a whole number as you would like to see, but close enough, right? Okay, that's certainly not going to justify that as a certain fraction. So this is about 3, that's about 8, that's about 1. So the empirical formula, C3H81. Very similar to the assume 100 gram reverse percent composition problem. As a matter of fact, the last step is also like a reverse percent composition problem. Sometimes they give you the molar mass, and then they go, what's the molecular formula of the compound? Well, you can take the molar mass of the whole thing, and it's called the multiplier for the empirical formula. If the empirical formula is this, when you add that up, 3 carbons, 8 hydrogens, and an oxygen, you will get approximately 60.11. When you divide those out, it's 1. So sometimes, that might be 120, and then you'd have to double everything, okay? Or if this was 180, you'd have to triple everything. But in this case, it actually worked out to be a ratio of 1. So the empirical formula equals the molecular formula, and looks like you might have like a good old propanol, probably isopropyl alcohol, rubbing alcohol, is probably what this unknown compound was. And all you had to do is heat it up, absorb out the CO2, and, you're burning it, basically, combustion. You get that CO2 absorbed, you get the water absorbed, and then analyze it. Okay? So there'll be a couple of practice problems with the answer key for you to practice combustion analysis. And we want you to know how to do that, and that is your short lecture on our final application within stoichiometry is doing a combustion analysis problem. Some other good examples when you look at the problems. We'll just do the combustion analysis problems from this little section. All right, so if you're wondering why this was example 3 and 4, there was some other stuff that we had already done, like a reverse composition problem, and I don't expect you to do those again. So that's the end, and this is actually the cutoff point where the test is coming. Some of you got a lab to do yet, and at any rate, we'll talk a little bit about what you can expect on the test on Thursday. Okay? All right. Sounds good. And end of stoichiometry mini unit.